This is 3.4, page 4 of 12. On this example we've been using for this rectilinear motion, if you want to see what the motion looks like on the calculator, here's a couple of settings. First of all, if we go to Parametric Mode and put in the function into x1 and put y equals 2 into x2, what that will do is, remember, Parametric Mode, it graphs these ordered pairs, right? So it will graph, the x-coordinate will be basically the original y value of this cubic function. The y value will be 2 every single time. So basically it will graph on your calculator a horizontal line at 2 with the movement that's created by this position function, as if it were just graphing along a number line. I went ahead and I set up these window settings in Parametric Mode. So if you want to mimic what I'm doing here, you can do that. So here is my Parametric Mode all entered into my calculator. So I'm going to go ahead and hit graph, and you'll see that it's going to start graphing. And if you notice, it stopped and then carried on. Since it's graphing right on top of itself, it's kind of hard to see what actually happens. I can do second drawing, clear drawing, and watch it again. So you could do that as much as you want. I'm interested in seeing more detail about what happens. So one of the things you could actually do, go to your y equals screen, move to the left over here, and if you hit enter, it'll scroll through some graphing options. That'll graph a thick line. This one, a line with a circle, will actually show you each point as it graphs, or it follows the path of the graphing. So I'm going to select that. I'm going to hit graph again, and this time we can watch and we can see what's happening. It stops, it goes backwards, and then resumes and speeds off the page. So even though you can't see that, once it's done, we can watch it. We can watch it happen. So that's pretty cool. The one that I like to do for fun, if you go over here, hit enter one more time, it doesn't have the line, it's just the circle 0, and that's the invisibility cloak version. If you hit graph, you can see where the values would be. You can see it back up, and you can see it go off the page, and it's off the map. Anyway, that's kind of interesting to watch that graphing. Okay, the main use of the position function, the velocity, and acceleration information is to find out what the motion of a particular particle is at any point in time. So what we're going to do is we're going to consider a particle moving along a horizontal line according to this function, this position function, and I want to describe the motion of the particle in detail, which means I want to know what its position is with respect to the origin. I want to know what direction it's moving. I want to know when it's not moving. I want to know when it changes directions. I want to know when velocity is increasing, when velocity is decreasing, when velocity is constant, and I want to know what the speed is. So in order to tell all of that, we're going to look at the position function, the velocity function, and the acceleration function, and analyze the information we can get out of that. So, if we're describing the motion of this particle in detail, the first thing I want to consider is the position. I'm interested in when it's at the origin, and when it's to the left of the origin and to the right of the origin. So I need to know the times when it's at the origin is when the position function will equal 0. So basically I need to factor this. So the first thing I'm going to do is take out this coefficient. I don't particularly like coefficients. So I'm going to factor out at 1/6. That leaves me with t cubed minus 12t squared plus 36t minus 12. And now I need to factor this. Well, of course, this is not something you could factor by hand. You can find the zeros on the calculator, and that's what I'm going to do. I'm going to go ahead and set that up. Okay, so here I've entered my function in the calculator. If we do zoom standard, since it's a qubit function, we are expecting up to 3 zeros, and we do have 3 zeros. So I know I could factor this into 3 sets of binomials. With t cubed, I know there's going to be a t at the front end of each of those. Since all the zeros are going to be positive, I know that my binomial will look like t minus some number, t minus each of those zeros. That way when I use the zero product property, I would solve each of these for t and I would get a positive number each time. Okay, so second calc, 0. I'm going to find my left boundary. I'm going to move to the right to find my right boundary. Hit enter for my guess, and I can see that the first 0 is at 0.380 if I use 3 decimal places. Okay, and I would do a similar thing for the second 0 and the third 0. I'm going to go ahead and just fill in those values. The second 0 is at 4.337. The third 0 is at 7.284. So those are my 3 zeros. And I'm going to do a sign analysis because what I'm interested in is whether or not to the left and right of these zeros, the particle is to the left of the origin or to the right of the origin. So I would need to know the sign of this function at those intervals. So I'm just going to start out by labeling the zeros. Remember, those are the parts, those are the times where the particle is at the origin. I'm going to label this with an S just to remind myself that I'm dealing with the position function. So in the sign analysis, what you want to do is just find a value that's in an interval, plug it into the factored equation. I should have put equal 0 on that. And take a look at the signs of each of the parts. So on this one, I'm going to plug in t equals 0. So the 1/6 is positive. 0 minus 0.380 is negative. 0 minus 4.3 is negative. 0 minus 7.3 is negative. So a positive times a negative times a negative times a negative is overall negative. That interprets to left of the origin. I'm going to pick a value in between 0.38 and 4. So I'm just going to pick t equals 1. Plug this in here to get the signs of each factor. The 1/6 is positive. 1 minus that would be positive. 1 minus 4 would be negative. 1 minus 7 would be negative. Overall, this is positive, which interprets to the position being right of the origin. A number between 4 and 7, I'll take 6. Positive 1/6. This binomial is positive. This binomial is positive. The last binomial is negative. The negative overall interprets to left of the origin. And finally, a number bigger than 7, I'll use 8. 1/6 is positive. This binomial is positive. This binomial is positive. That binomial is positive. Overall positive, right of the origin. So at any point in time with this sign analysis, I could see where the position that the particle is with respect to the origin. Any point in time, 5 seconds, it's going to be left of the origin. At 0.25 seconds, left of the origin. At 10 seconds, right of the origin, and so forth. Okay, so that'll describe part of the particle's motion. Next, we want to look at velocity. And if you remember, velocity is going to tell us something about the movement. Velocity is negative, means it's moving to the left. Velocity positive, it's moving to the right. Velocity is 0, it's, for that instant, it is still, and perhaps it's changing directions. We'd have to take a look and see. So what we want to do is look at velocity and find out where the zeros are. So velocity is s prime. I'm going to go all the way back up to the original equation. That's the best one to get the derivative from. So if I take 3 times that, I get 1/2 t squared minus 4t plus 6. I need to set that equal to 0. I'm actually going to factor out that fraction again to make my factoring easier. If I take out a 1/2 there, that leaves me minus 8t plus 12 equals 0. I believe this is t minus 6 and t minus 2 equals 0. Zero product property gives me two solutions. Time equals 6, time equals 2. I am going to build a sign analysis on velocity and put my 2 times there in numerical order. Time equals 2, time equals 6. So those are the spots where velocity is 0. I want to look at either side of those and see what's happening with my signs. So pick a value smaller than 2. We'll go with 1. I'm going to plug it into this level, factored level. So I get a positive 1/2. I get a negative binomial there. I get a negative binomial there. Positive, negative, negative gives me overall positive. And a positive sign on velocity tells me it's moving right. In between 2 and 6, how about t equals 3? I got positive 1/2. I've got a negative binomial there. I've got a positive binomial there. Overall negative. Moving left. And bigger than 6, we'll go t equals 7. Positive 1/2. Positive binomial. Positive binomial. Overall positive. Moving right. So 2 places where the velocity is 0, and also 2 places where it's changing direction. Okay, the third piece is acceleration. By looking at the sign of acceleration, we are able to tell whether velocity is increasing or decreasing, or see if it's constant. So I'm going to look at acceleration. That is the derivative of velocity, or the second derivative of position. I'm just going to go right up to this equation here and get my derivative. So 2 times that is going to be just t. The derivative of that piece is minus 4. That's pretty straightforward. Set that equal to 0. I don't have any factoring to do. It's just t minus 4 equals 0. So I know my point that acceleration is 0 equals 4. And I'm going to look at the intervals on either side. So let's plug in t equals 3. And we just have one term to plug it into, or one equation to plug it into. So we get negative. The negative acceleration interprets to decreasing velocity. And let's see, above 4, we'll just take 5. Plug in 5, it's overall positive, increasing velocity. Okay. So we're going to take this information. We're going to take what we know about interpreting this information. You have that one sheet that gives you some guidelines. You do need to have those memorized. We're going to use this sheet with our guidelines for interpreting these values, and we're going to fill out the next page, which is our superchart.